Greetings, physics enthusiasts. It's lovely to see you today. Today, we're going to talk about a topic called relative motion. In AP Physics 1, Unit 1, Lesson 12. Relative motion is basically just motion, because all motion is described relative to or with respect to something else. Relative means with respect to. Sometimes that's abbreviated WRT. For example, if you look at my ring, is my ring moving? Well, relative to my nose, the ring is moving. How do I know? Well, the ring is to the left of my nose, and then the ring is less to the left of my nose, and then the ring is at my nose, and then the ring is to the right of my nose, and then the ring is righter than my nose. So its position kept changing. However, is my ring moving relative to my ring finger? Nope, 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 not moving. So it's at the same position at the beginning on my finger as it is in the middle on my finger as it is at the end on my finger. So with respect to what? The motion depends on what we are measuring the motion with respect to. That thing that we're measuring the motion with respect to is sometimes called the frame of reference. So if the frame of reference is my nose, the ring is moving. If the frame of reference is my finger, the ring is not moving. And you might think, well, that's kind of playing with things a little bit. But when you're on an airplane, going from here to Chicago, is my pen moving? Well, I'm on the airplane and my hand is on the airplane, the pen is on the airplane. It doesn't feel to me like the pen is moving. And relative to or with respect to the airplane, the pen is not moving. But relative to or with respect to the ground 5 miles below the pen is moving. So it's not just some mental game we play. It really does relate to the world around us and the way we feel things. So sometimes we can have some fun with this. Speaking of flying on an airplane from here to Chicago, once you get to Chicago, if you go to Chicago's O'Hare Airport, Chicago has a couple of airports. Midway is an itty bitty airport, but Chicago O'Hare is a big airport, and it has some of those moving sidewalks, which are really fun. Have you seen them? If you haven't, Google moving sidewalks in the airport. But you're walking along, and there's this long terminal. It's a couple 100 meters long, and there's these rubber strips that go for 50 meters along the airport, and you stand on the little rubber strip, and then you can stop walking because the rubber strip moves you along. So here's you moving along, but are you moving relative to the floor you're standing on? No, you're not. But are you moving relative to the terminal around you? Yes, you are. Those are really fun because, sometimes, people who are experienced travelers, they get on there and they walk. So they're walking relative to the moving sidewalk, and the moving sidewalk itself is moving relative to the terminal. Oh my goodness. So we've got this, it's this loop, and then the person is on here walking. So the person is walking relative to the moving sidewalk, and the moving sidewalk is moving relative to the terminal. How fast is the person moving relative to the terminal? Well, that becomes a fun physics problem. If the person walks at 3 meters per second and the moving sidewalk itself moves at 1 meter per second, is it obvious that the velocity of the person relative to the terminal is 4 meters per second? I hope the answer is yes. What if sometimes, kids or childlike adults, when there's not a lot of people around, will walk on the moving sidewalk backwards, the wrong direction? Have you ever done that at the mall? Run up the downscalator or run down the upscalator? And I was out at dinner a few weeks ago, yeah, and it was my husband's buddy's birthday party. Anyway, so she had this lovely birthday party at this restaurant, and then there was this parking garage where we had parked, but I wasn't very familiar with how the building worked, and I could not figure out how to get down to where I had parked because there was just this one escalator and it was going up. So I was up here at the top, and I had taken this escalator up. I didn't know how to get down there except to go back the way I came. There was no downscalator. There was just the upscalator. And so I looked around, there was nobody there. So I ran down the upscalator. I probably wasn't supposed to do that, but I did, and I got to my car. So anyway, so sometimes I go the other direction. So what if the little moving sidewalk is going this direction, but I'm still on it going this direction? Can you figure out what my velocity relative to the terminal is going to be? So in this situation, my velocity relative to the terminal is going to be 4 meters per second to the right. On this one, my velocity is going to be 2 meters per second to the right, because this is slowing me down. Now, this is us thinking about this intuitively and coming to the answer. And when I quiz you on this in class, if you just see the answer, you just know it and write it down, that's fine with me. But if you want something more mathematically precise, what I'm going to say is the velocity of some object A with respect to a frame of reference B plus the velocity of that object B, so the frame of reference is now the object that's moving, with respect to some other frame of reference C, that is the velocity of A with respect to C. So this is always going to work. VAB plus VBC equals VAC, where the two subscripts represent the thing moving and the frame of reference, or the thing with respect to which, the object is moving. In order to do this addition, it is required that these two things be the same letter. The B and the B being adjacent to each other just disappear. And the final answer is this AC. So how would I do this here? This is the velocity of the person with respect to the sidewalk. And now I'm talking about the sidewalk itself is moving, the velocity of the sidewalk with respect to the terminal. Gives me, the S's are adjacent, the velocity of the person with respect to the terminal. So velocity of the person with respect to the sidewalk is 3. The velocity of the sidewalk with respect to the terminal is 1. And that gave me the velocity of the person with respect to the terminal is 4. What about down here? I've got the velocity of the person with respect to the sidewalk plus the velocity of the sidewalk with respect to the terminal is the velocity of the person with respect to the terminal. The person is still moving at 3 meters per second with respect to the sidewalk. The sidewalk relative to the terminal now, though, is traveling to the left. So that's a -1. And 3 plus -1 is, you guessed it, 2. And that's why I got 2 meters per second. Both of these answers, 4 and 2, are positive, and that's why the direction there was to the right. Is that making sense to you? Hope so. Let's see if we can do something a little more fun, just because we're going to get more things involved. What if there's a train on some train tracks. So here's my train traveling along on the train tracks. And let's say that there is a person working on the train who is bringing food out to the dining car. And let's say that there is a dog, I'm sure it's a certified service animal, on the train as well. How do I know it's a dog? It's here's its little thought bubble. Woof. Okay, so we know it's a dog now. And now, sadly, the dog has a flea on it. So the dog is going to move along with a velocity of 2 meters per second, and the flea is walking along on the dog with a velocity of 1 meter per second. Oh my goodness gracious. And then this person is walking very efficiently along the train at 3 meters per second. And sadly, there is an ant on the tray. Well, that's unfortunate. That food's going to get sent back. But the ant is traveling at 0.5 meters per second. Goodness gracious. Well, that's a lot going on. So I could ask you all kinds of questions. But the questions I ask you all have this format. What is the velocity of some noun with respect to some other noun? And so there's worker, ant, dog, flea, train, and train tracks. How many things was that? Worker, ant, dog, flea, train, train tracks. There's 6 different nouns there. How many ways could I fill in these blanks with 6 different nouns? Well, anyway, that's a math permutations question. But anyway, you could write this question a bunch of times and just fill in noun, noun. Person, ant, person, flea, person, dog, person, train, person, tracks. Ant, flea, ant, dog, ant, train, ant, tracks. Right? And so dog, flea, dog, ant, dog, person, dog, train, dog, tracks. Lots of different pairs of nouns you could put in there. Now, the answer is always going to have a number, some number, a unit meters per second, and then a direction, which is either going to be to the right or the left. Make sure that your answers always say a number of meters per second and then a direction, either right or left. So feel free to play with this as much as you want, but I'm going to show you one example. Let's pick the flea and the ant, just for fun. What is the velocity of the flea with respect to the ant? So I'm trying to find velocity flea ant. How fast the flea is moving relative to the ant, assuming the ant is our frame of reference. So I want to start out with the velocity of the flea with respect to something. Now, I only know the velocity of the flea with respect to one thing. That's what's given, is the velocity of the flea with respect to it's a dog. That's what's given, 1 meter per second. And then my second velocity has to start with a d. It was a d second here, so I've got to have d here. And the velocity of the dog is given with respect to the train. Oh. Now, this is what's weird. The velocity of the train with respect to I'm going to call this person. This is the one place that we're going to have to do a little bit of thinking. I'm going to put that off for a moment. But I'm indicating that we're going to talk about that in a second. The velocity of the train with respect to the person, and then the velocity of the person with respect to I have to start with person, right? Ant. I started with F, I ended with A. I started with F, I ended with A. And the DD get erased or thrown away because they're right next to each other. The TT get erased because they're right next to each other. P and P get thrown away. So if I know these four velocities and I add them together, it's going to legit give me the answer. What is the velocity of the flea with respect to the dog? 1. What is the velocity of the dog with respect to the train? -2. Do you see why I made it a -2? Because the dog's traveling to the left and the flea is traveling to the right. All right, now, velocity of the train with respect to the person. It turns out that VA sub B and VB sub A, how fast A travels with respect to B and how fast B travels with respect to A are the same fastness, but they're in opposite directions. The velocity of the ring with respect to my nose, the ring is traveling to the right relative to my nose. Well, did you just see that my nose traveled to the left relative to my ring? My nose started out on the right of the ring. Now my nose is to the left of the ring. So my nose traveled to the left relative to my ring. So this is very important. The velocity of an object relative to a frame of reference is the opposite of the velocity of that frame of reference relative to the object. So what's given in the problem is the velocity of the person relative to the train, 3 to the right. If the velocity of the person relative to the train is 3 to the right, the velocity of the train relative to the person is 3 to the left, -3. And again, look here, the velocity of the ant relative to the person is what's given, -0.5. That's the velocity of the ant relative to the person. Well, I want to know the velocity of the person relative to the ant, so that's positive, 0.5. Make sense? So there's different parts here. Do you see that the velocity of the flea with respect to the ant, or the velocity of the flea relative to the ant, how fast the flea is moving if the ant is the frame of reference? I said the same thing 3 different ways. FA, velocity of flea with respect to ant. Do you see that that should be the sum of these 4 individual velocities? Because I started with F and I ended with A. Started with F, ended with A. As long as D and D are next to each other, T and T are next to each other, and P are next to each other, they go away. So if you see that this is the same as this, and this is the same as these 4, we're doing well. These 2 velocities were given 1 meter per second, the velocity of the flea with respect to the dog, -2 meters per second because the dog is traveling to the left relative to the train. And then these 2 velocities are not given. What's given in the problem is the velocity of the person relative to the train, not the velocity of the train relative to the person. That's why instead of +3 to the right, I wrote -3. And the velocity of the person relative to the ant is not given. The velocity of the ant relative to the person, -0.5 is given. That's why I wrote +0.5 here. And then I just have to add these. -3 and -2 is -5, plus 1 is -4, plus 0.5 is -3.5. And instead of -3.5, I'm going to call that +3.5 meters per second. The negative means to the left. And then, like I said, all answers have a number, 3.5, a unit, meters per second, and a direction to the left. That is how we do relative motion. We'll do several more examples together in class. And of course, we'll do a practice quiz, and then we'll do a real quiz. Lots and lots of fun. As you know, the fun never stops in physics. See you soon.